Hey everybody, Mr. Newland here. Let's talk about how we can take the distances and periods of the planets in our solar system given in AUs for distance and years and period, orbital period, and linearize the data. Hopefully you can see the columns of data here. P1 being the 8 major planets periods measured in Earth years, and A1 being the 8 major planets distances from the sun measured in astronomical units. You can't work with the constants that we typically use in astronomy without working with meters, kilograms, and seconds, or the SI units or MKS units. So like for example, the gravitational constant from Newton's universal law of gravitation is written here in box number 3, 6.67 times 10 to the negative 11th. But the units, which are not listed here because you can't do units in Desmos easily, the units are in MKS. So we need to convert these times into seconds and these distances into meters, which can kind of ridiculous numbers in astronomy, but it is a common task and it's one that we should probably learn how to do. So I've already entered, you can see the data is there, and make it a little bigger. You can see the data is there already in the columns. So feel free to copy that down. I've typed in the constant for G, and you know what, just because I feel like I can repeat this process, it was 6.67, and then asterisk 10 caret negative 11, like that. So that's the easiest way to turn things into, I'm going to save my work, easiest way to turn things into exponents. And then for this D sub AU, I'll go ahead and redo that whole line. D underscore, now I'm in underscore mode, AU, and to get out of underscore mode, I'll hit the right arrow key. So I'm back into type mode. And the constant was 1.5, again, asterisk 10 caret 11. And I'm not going to do this for all the other constant, but there's the one for the sun. The cool thing about this process is column A1 and column P1, those are lists, but I can, on this one line here, take column A1, which is the distance measured in astronomical units, and I can multiply by D sub AU, which converts from, if I multiplied any one of the numbers in that list by 1.5 times 10 to the 11th, when I'm doing it, I'm converting that one distance from AUs into meters. The cool thing about box number 7 right here is it's doing that for all of the items in A1. So even though I'm not explicitly telling Desmos to do that, if you take a list in Desmos and you multiply that list by a single constant, it actually goes through each of them and multiplies each of them by the constant, and now it's in a new list called A2. So A2 is now all of the distances, but those distances have been converted from AU into meters. And I'm going to do the same thing with my other list. So P1 times the number of days in a year, because P1 is currently in years and we want it in seconds, times hours per day, times minutes per hour, times, I lost the asterisk, times number of seconds in a minute. So we're really doing dimensional analysis with box 7 up here and box 8. We're multiplying each of the elements in A1 by the number of meters per AU, and you can think of the AUs as canceling out left in meters. Same thing here. This is years, and that's days per year, so the years cancel, so I've got days, and then days per hour, and then hours per minute, and then minutes per second. So I'm left with a list of 8 periods for the planets in our solar system, but converted into seconds. So we have the data in the right, I'm going to hit save. We have the data in the right units, we have all of the things we need, but in order to linearize, which means when we plot our one of our variables on the horizontal axis and the other variable on the vertical axis, the data will actually show up as a straight line. And the only reason we do that in science is so that we, as science students and math students, we're pretty good at working with slopes. And we can actually take that slope and turn it into something meaningful. In this case, we're really practicing this process so that we can do this for a different, completely different solar system. That's the real purpose of doing this exercise, is to take the distances and times of our planets, solar system data, and convert it into meters and seconds, so that we can actually calculate the mass of an unknown star. So that's why we're doing this process. In order to do that linearization thing, though, we need to figure out what we want to be on what axis. So there are multiple ways to do this, but the way this particular problem is set up, you can see right here, you know what we're going to do? We're going to move the t squared out, y'all, and I'm going to put it on the outside so that we can think of this as, here, I'll put square brackets there and there because I want to highlight it. This little chunk that's in square brackets, all that junk is a constant. Big G is the universal constant for Newton's law of gravitation, which I have up there. M is the mass of the star. In this case, that's going to be M sun. Then obviously 4 and pi are constants. So what if we let the thing on the left-hand side, this r cubed, what if we let that be our y variable? But instead of radius, we should think of it as a2, which has been converted into meters. So a2 and then cubed. So what that does is it takes all 8 of the distances to the planets in meters and it cubes them. And instead of thinking of that list as a cubed, it's now a new list of y values. So y1 is now 8 y values that we can plot. And we're going to do the same thing with x. And on the x-axis, and we need to scroll, look at our comment here, the t squared is what we're thinking of as the x. So look, it's y equals m times x, and if there was a y-intercept, there would be a plus b. Again, we're linearizing our data, so when we plot it, the slope could be used to calculate, in this case, the mass of an unknown star. So we're practicing with one we know so that we can do this with another one. So let's take the times, the periods that have been converted into seconds, and we'll square them. Don't forget that Kepler's third law is p squared equals a cubed, and right here is the p squared. The t, it's considered t here, which because we switched it into seconds, and a is considered r, but it's a cubed is r cubed right there. So now what we've got is a completely different representation of our data. We've taken all of them, I'm going to save my work, we've taken all of the times and positions, and we have turned them into, let me scroll down here, we've turned them into data that we can turn into a straight line. There's more to unpack from this. We're not really, we're going to do a little bit more with this process, but today when we were working with this, I thought it would be helpful to show you how to do this process with just the planetary data in our solar system. And I think I'll actually go through the algebra related to this slope thing, either in another video or in person. But the interesting thing about this is that the y-intercept and the slope can be used to calculate something useful. But the main thing I wanted to do in this video was to go through how we could put data into a table, do some conversions, and actually store the data into lists. And in another video, we'll talk about how to actually get that to plot. Okay, I hope that's helpful.